But we're not done yet. There's still another problem. For example, in this simple graph with 4 web pages represented at 4 nodes and some links, we can write down the H matrix. Okay, it is again 4 by 4, and you should be getting better and better at this already. The H matrix simply looks like this. And you can easily see that depending on what is my initial pi vector, I will end up with different importance score vectors. In other words, there are too many, more than one consistent importance score vectors. Indeed, if I start with, say, initialization of 1, 0, 0, 0, 0, then I end up with the importance score being half, half, 0, 0. However, if I start with initialization of 0, say 0.3, 0.70, then I end up looking at importance score vector in the end as 0.15, 0.15, 0.35, 0.35 for these 4 web pages. So what we really want is to say that if you give me a matrix and I keep doing the iteration pi transpose equals pi transpose that whatever matrix might be, H hat, starting from any initialization vector pi times 0, I should be able to converge, meaning that after sufficiently number of rounds of this, then I can be arbitrarily close to a particular fixed vector pi star. Okay? But this example shows that that may not be always the case. So here is a possible solution, and this solution illustrates actually a very important theme, randomization, that we'll be encountering quite a few times in very different contexts in different networks this course. This is the very first encountering of that randomization idea. It says that, you know what, if you're on a particular web page, a node in the graph here, you may be hopping to the other nodes that's hyperlinked from this node with evenly likely chance. For example, if there are 2 of them, 1/2, 1/2. But this whole behavior may be only theta % of the time you follow. And 1 minus theta, where theta is just some number between 0 and 100 in percentage points, the other 1 minus theta % of the time, you actually will do a random flipping of the web pages. Okay? So following the embedded outgoing links is only part of the model of the navigation behavior by users on the web. It represents, say, theta %, and 1 minus theta %, you will be doing a random picking. It turns out that what theta you pick determines quite a few things, including the rate of convergence. Smaller theta gives you faster convergence in general, but smaller theta also means that you are pretty much ignoring the connectivity pattern of the hyperlinked graph. So that's not too surprising. It turns out that we tend to pick 85% or 0.85 as the right trade-off between relevance of the connectivity pattern and the speed of convergence. So how do we model, back to this random flipping of web pages? Well, we're saying that here is a big matrix, which is really 1 over n, 1 over n, 1 over n, 1 over n, dot, 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 and 1 over n, 1 over n, dot, dot, dot. And every single row is just 1 over n, which we can write as basically a matrix of 1, 1, 1, 1, 1, 1, 1, 1. Everywhere is 1 divided by n, which we can write as simply 1 over n times a vector of 1, outer product with a vector of 1s. Again, outer product may sound a little weird to you, but you can write down a simple example, say a 2-dimensional example. Okay, 1, 1 is a column vector, outer product with 1, 1. So 1 by 2 times 2 by 1 times 1 by 2. You get a 2 by 2 matrix, which is 1, 1, 1, 1. Okay, so one outer product with one column, then row vector normalized by 1 over n is exactly what we want. So the third matrix is simply 1 minus theta times normalization 1 and this matrix of all ones. Vector 1 outer product with vector 1. And then don't forget the original theta percent of the time you will follow h, or better still the modified h hat. And this plus this is what we call the Google matrix, represented as G. Now don't get confused with the Gij back in lecture 1 in cellular network. Okay? That can also give you a matrix G. There are interesting striking parallels between the two, but not stemming from the confusion of the symbols they use. So this matrix G, the Google matrix, is the sum of two matrices. We know this matrix is nice because it's the sum in turn of H, which is sparse, and a rank 1 matrix for the dangling nose. And this obviously is a rank 1 matrix as well. It's a very simple matrix. So G is the sum of a large and sparse matrix plus two large and rank 1 simple structured matrix. So now we're ready to describe the very famous PageRank algorithm behind Google, and one of the reasons for Google's success on the technical side. It says that given this matrix G, which is H, okay, plus 1 over n times W vector times outer product with one vector, the whole thing theta percent of the time plus 1 minus theta, the other percentage of the time, is multiplying by this randomization vector, okay, giving you an outer product of matrix of all ones. Okay, you define G as such, and then you're going to iterate. Pi transpose at time k plus 1 is simply the last iterations pi transpose, all these are vectors at iteration k, okay, multiplied on the right, not by the H matrix anymore. We got to modification we needed by matrix G, and let k keeps on going, and you are now actually guaranteed to converge from any initialization pi vector to the equilibrium transpose equals pi star transpose times G matrix. In other words, the importance score is actually the dominant left eigenvector of matrix G, not just H. We're skipping the proofs in linear algebra, but the end result says that with these two modifications we can guarantee a convergence to a uniquely defined left eigenvector with eigenvalue 1 relative to this matrix G. And this can be either computed if G is small enough directly, or iteratively through this procedure, iterating over index, iterations indexed by k. Now, if you still want to take the two more remaining steps, then you'll be done. One is you want to normalize. Remember, so far we haven't normalized this pi vector yet. Okay, if you really want to know the relative scale, you want to normalize them. So the new pi I is really the original pi I divided by the sum of all the pi's entries. But the most important thing is actually ranking now. Remember, we started with ranking, not computing scores. Computing score is a means to the ends of ranking. And ranking says, then you can look at either the normalized or the not normalized version of pi, and then whichever node has the highest pi is ranked the highest, then the second, then the third, and keep on going. And the top 10 will be going on to the first page of the search results. And you can see that if ranking is what you care about, actually you don't exactly see the relative scale. For example, this might be way more important than 2, which is only slightly more important than 3 by this computation of importance scores pi, but you wouldn't know. Okay, Google doesn't visualize that scale, And perhaps that's a good idea because that scaling may not be that robust. And hopefully the ranking itself is more robust. So in summary, we have constructed 3 matrices from H to H hat to the whole Google matrix G, and this iteration plus maybe normalization, and finally our ranking is how, roughly speaking, Google displays the ranks of the web pages.